So glad to be here. This has been the most challenging talk for me to prepare. Not that I'm anticipating to be any good, but it's been very challenging because of the landscape of algorithms which I participate in and the wonderful work that's going around. So I try to give my best shot. Many of the slides are new, but to celebrate that level of complexity on this landscape, I'm just showing some of the toys I've worked in the last 9 years or so. And also coming from a computational background, back in my PhD, where I kind of was a bit frustrated of just doing simulations, I went on into a spree of designing robotic systems, helping to spin off a company that does some of these toys and collaborating with agencies, especially in the US. So I'll start picking on the, supposed to have some volume here, on where I left off in ICRA 2018, which some of you might have been there, where we had take task-based feedback controllers, also called whole body controllers, and bring them to passive ankle bipedal locomotion. It's a very hard problem, especially because of uncertainty. And we had developed what we thought it was new, which is called time velocity reversal, which ended up being something very similar to regular controllers. And we can see here a bunch of people from CMU and from the Army Futures Command are using our robots. But overall demonstrates the capability of these robots to do whole body control at runtime with uncertainty and with the speeds that we're looking for. During those times, after IRIS, we extended with bias time to velocity reversal algorithms, and we're able to walk directionally. The robot cannot really turn, but it can go in all directions. Uses IMU and also motion capture, and also handle rough terrain. And although we've seen wonderful robotic systems here, this is the only task-based approach that I've seen that it runs in passive ankle bipedal robots, and we're proud of it. So next frontier for people like myself, I'm inspired about the intelligence of and the blending of geometric techniques with reasoning systems, and as well possibly the cognitive level. So what is whole body control? This is all it is. It's really a multi-goal sensor-based feedback controller where we feed sensors, inertial, vision, to task-based controllers and control this entire whole body behavior. It deconflicts maybe some of your trajectories, even if you do them with optimal control, with assurance of visibility, maybe they're off, and at runtime they're going to conflict. Maybe it's a context switcher and a task switcher that allows for smooth transitions when you decide to do different things. Or maybe it's an NPC or an optimal control where you generate entire trajectories in every possible way. As you can see earlier, it can be a locomotion algorithm, or it can be combined with locomotion algorithms. And then what we'll see today, it can be also used for strength amplification, for asymmetric, nothing else than non-periodic exoskeletal applications. So my take on humanoids, and I know there are different opinions here, to me they are not distance runners. That we have vehicles with wheels or with tracks. They're meant to live in tight spaces. I'm really inspired by living in space habitats, in boats, in ships, in homes, in construction facilities, in inspection facilities, and so on and so forth. We have traded horizontal footprint by vertical footprint, and arguably there's a lot of things that quadrupeds could do. Maybe the human form, it has to be connected to the social aspect, and the fact that we are reflecting our own image in that anthropomorphism. So I think that although we don't talk too much about it, the anthropomorphic aspect is very important for the cognitive level, and other things that we go on future algorithms that might involve intentional recognition, and then other ways to connect with the human that is not necessarily geometric only. Bipeds are hard. They fall often, and that's the fear of everyone. They fall because the center of gravity often is leading the leading foot, or about the same length as the leading foot, and then the trailing foot gets stuck, stumbled with an object. The solution is to have the center of mass always behind the living foot. This is not my idea, this is Dennis' own idea, or maybe some other person, right? But I do sign on it. Maybe out of the 100 walks that Kevin Berry showing here, we should walk sideways. And that's absolutely fine, because these are not distance runners. These are guys that are going inside homes and really connecting to the environment and rubbing shoulders in crowds and so on and so forth. So I'm not here for speed. So again, connecting to the intelligence from a top-down approach, the problem with humanoids and many others is how to tell them what to do. It's not an R2 problem, and especially by non-expert operators. So a new project sponsored by the Science of AI and Human-Robot Interaction addresses these. This video is by my copy, I Thinking Robots. The operator is telling the robot, is teaching it with verbs and nouns and adjective and semantics, teaching it to squat, and the robot doesn't know how to squat. It knows what is lifting the arm, but it doesn't know what means crouching. And another robot knows what crouching is. And there's all these convoluted informational processes by instruction, and that's fine. That's one way of telling robots what to do. So what kind of information we can turn into symbols? Well, we have to try. A lot of it. The environment can be turned into symbols in a geometric sense. Our multi-agent, multi-appendix coordination system can be turned into symbols. Our controllers can be verbs, can be symbols themselves. In this case, for instance, keyframes from Locomotion. And now we can reason in kind of a reactive synthesis way. Always, when the human appears, then choose that appendix, or that appendix for stopping. Or always that you're using that controller on the bottom left, and the next step is that geometry. Then use that quadrant of controllers. That's another way of telling robots what to do that I think we should consider also for this complexity. And those are the behaviors that emerge from that process. Navigating this intelligent locomotion, I have talked about it several times. That's one of the things we wouldn't do besides the cognitive level. Here we see the liveness of that process. On the right upper side, we see the environment acting as an adversary. And on the bottom, we see the actions, the multi-agent appendage thing. And then we see the controllers being chosen with these rules and then navigating this environment. So from symbols, how do we turn that into trajectories? Is whole body optimal control possible? And we've seen a lot of examples. Our approach is to sample the robot join state and solve a QP with all constraints, including contact and input constraints, emulating what we do in narrow space where we have warranties, and find the physical set of states, psi hat. We project joint samples to output space, for instance, controlling R3 of the center of mass, and discard unfeasible output goals early on at fast speeds. We project the physical joint states to output space, our task, discretize the space, and then we formulate an MDP where the transitions are given the number of successful states that can go to the next box in your discretized space, and that becomes waypoints. And finally, we do continuous space reachability analysis, where we can go from the boundary of one box to the next one, and that generates entire trajectories at runtime. Well, runtime, not quasi runtime, okay? So, if here we do full state propagation, we blow the machine, the memory, we are exponential. That's the first one couple of iterations, we blew up the machine. So if we do now boundary state propagation, we are now linear in complexity. And it only takes a couple of minutes to solve a strict input warranties, sort of R-space level optimal control, optimal whole body control process. It's all like whole body trajectory generation with contact input constraints, the solution for control humanoids. Maybe we're still running at minutes. We see talks here about accelerating that process, wonderful. But give it a few years, and that would be an MPC, much the same way that whole body control, for instance, running my DSD, it was an out-of-reach type of algorithms, and today it runs at milliseconds, even at sub-milliseconds. In the meantime, for agile feedback control, human and robots, the best solution is feedback whole body control. Here, task trajectories are computed a priori on simplified models without input constraints. such as constrained SE3 models or inverted pendulums or C-space planning, we consider then two mechanisms: hierarchical task sets and multi-contact transitions. And current trends that we see, they rely on hierarchical control problems with sensor-based tracking controllers as the main mechanism. And this is key because even if trajectories are offline feasible, even if you MPC offline, home planning, once you implement it in the real system, you're always going to be off. So you need to take very quick instantaneous decisions, and that's what priorities are for, is to let something go instantaneously in the name of continuing going and operating. In addition, changing task sets or contexts at runtime is a delicate feedback control proposition. So here we consider continuity of acceleration space, and we switch with these red bands. It's a feedback controller, sensor-based feedback controller, and then we switch using activation functions. We can switch also to another controller, is the blue line, and we can do it also in free form, as in the right-hand side. That kind of line of smoothing transition is now happening in many places. My lab happens to be one of them, but it's a wonderful area of warranting, reduce jitter and jerk in doing our performance. So if we don't use whole body optimal control, how do we generate trajectories? And I will use this opportunity to show our new biped Draco. It's based on liquid-cooled viscoelastic actuators in the name of being very lightweight and also tolerating very high payload, which is one of the things that we want to enjoy in human robotics. One way to address the planning problem is to use older models. In this case, inverted pendulum is x double dot equals omega squared x minus p. If q is the state, we can transform this into a quantized linear transition system where p is the position of the foot, quantized by the number of steps, and then we can use p as a feedback stabilizing process. There is no secret there. Very similar to remote controllers. Our solution for that is something called time to velocity reversal. It's very simple. We reverse velocity at t prime, and that gives a solution for the foot position that is a function of the state. And now we solve it. We have here the linear closed loop system. It's very simple to stabilize by just using the right eigenvalues. No secret there. The difficulty of implementing that in real robotics is to perform an uncertainty analysis. So we produce here a second order transition system now with foot position, landing uncertainty, eta, and also with state estimation uncertainty, delta. We don't know those values. We're going to poke the system around. We do a two-step contraction analysis, and we found that this is at the pole of uncertainty. We don't know where we are there within the convergence of our algorithm. So if we consider our state space, the blue ribbon, the light blue ribbon is all the states that are recoverable. And then if our region of uncertainty, this blue ball or red ball, is small enough, it falls into where we are, where everything is feasible and stable. So we have to fight for having our uncertainty landing the foot position at 1.5 centimeters and 2 millimeters for the state estimation. If we build so what we do, we go back to our robotic system, we rebuild it, we ensure that we have these latencies, these mechanical properties, and then only then we can achieve robust locomotion. But along the way, how does whole body control look in the real world? There is much heuristics to the point that we give up in dynamics and we go into inverse kinematics with priorities. For instance, the elevation and the attitude of the body has higher priority than the swing foot. Priorities become useful again because they play a role in your stability, in your bandwidth of the task space. And this is an area that is completely unexplored, but I do encourage everyone to explore it. Priorities as a means for achieving better real-time capabilities. This goes into an inverse dynamic process where we compensate for gravity, and also we smoothen contact transitions, we reduce jerk, and finally we go into an impedance controller with torque feedback, and that achieves stable locomotion. You see here Dong Hyun a few months ago tried that in Draco, stabilizing it with a Steam 300, and then arguably this is infinite stepping, so the algorithm works pretty well using based on the principles of task-based controllers, of whole body control. And this means that now we can add other output functions. We can control the upper body as well. That's what the philosophy of object control is about altogether. So let's move on to exoskeletons. Thus, whole body control translate to exoskeletons. Worker augmentation exoskeletons have two main tasks. One is gravity compensation or offloading the payload, a backpack for instance. And the second is strength amplification, and via calf sensor feedback. So here we have Sajid. It's an exoskeleton designed by Aptronic, a company I had to co-found. We have one of our mechanical engineers here who's designing the upper body. We show here the real lower body. There is also a real upper body that I cannot show right now. The lower body has abduction, flexion, rotation, flexion, roll, actuators. Some of them are passive. It conforms very much to the human ROM, and it is very comfortable to wear. It has cap sensing on the ankles. It has cap sensing on the waist, cap sensing on the upper back, and that detects the tension, and it can be used for strength amplification. The upper body consists of a waist rotation, as well as a coronal rotation, and then we have a shrug, which is gravity compensated, and then we have a rotation of the shoulders that conform to the anatomy of the body, and then we have flexion of the shoulders, and then maybe in the future we'll have also flexion on the elbows, and that's designed for logistic operations. A wonderful device and an R&D product of this company. We have sensorized FSRs on the soles, as well as cap sensing. We see the inserts that go inside the shoe, and all the reaction forces go through the shoes. Very neat. Aptronic has designed a wealth of actuation systems from our classical linear bolt screw serious elastic actuators. This type of them are really cool for increasing power density. We have now also rotary pancake liquid cooled devices, also high power density for the abduction and flexion of the hip. And then we have CAN actuators as well for the shoulder abduction and flexion as well. All of these augmented with a network amplification system called Axon, and that's how we create our embedded system, whatever it needs to be. That's the network of Megatronics. We have a root node, we call it medulla, all the amplifiers, network amplifiers, and then we see the pancake, the linear, liquid cool. Up there we see the reservoirs for liquid cooling, and that allows, liquid cooling allows us to have a very light weight, I think it's about 70 pounds, 30 kilograms in the lower body, and allows to lift up to 30 kilograms of weight on top of the weight of the arm exoskeleton. Our approach for control started with plain vanilla whole body control as a QP, and slowly we turned into an LP type of problem. Actually, Gray here is the architect of this technology. It allows us to impose priorities as a linear program in much better way. We formulate the statics as the constraint, so not dynamics as Frank was talking about. So here we have the dual contact case. F0 are joint torques, your actuation projected into the waist, and FC0 is the reaction forces picked from the user, and then amplified now by Kp plus 1. This filter that we have here, we have to consider the filtering, the frequency aspect of your gains. You want to have maximum gains, so your exoskeleton not only does gravity compensation, but follows you. As you move, it follows you with the maximum bandwidth. It amplifies your strength, or follows your arms, right? But there is a limit of how much amplification and high frequencies you can achieve. So we have to turn it down before we hit the maximum compliance of the human. The human impedances, the human damping is very important. We have a site of the lab that does identification of human impedances as a function of the damping, as a function of the stiffness. And only when you do that, you can maximize your strength and at the same time be stable. And then the term on the right-hand side is the differential forces, is the internal forces between the feet the cap forces there. We're not trying to impose forces, we're trying to follow what the human wants to do. That's what the exoskeleton does, follow as well as possible by lifting the gravitational payloads. So here we see the system in action. That's one of our operators. You can see doing some fairly complex maneuvers. One of these only exoskeletons that can do that by lifting up to 30 kilograms. One of the comments I get is that the exo seems to do nothing. After all, the operator is walking normally. And then my answer is precisely, that's what is difficult, to retain the traits of the worker and do it while amplifying forces, strength, and while mitigating payload. So you're going to see more there on this run, and I'm really excited. And I believe this is going to be almost my last slide. The flavor of this workshop is just wonderful. It's longitudinal studies of legged robots. The closest thing that I'm involved with is with NASA through the years. Steven, one of my students, still is there actually full time nowadays. Valkyrie is an ongoing program. And then one of the things I get from Valkyrie, they use it in kind of longitudinal studies, number of times, days, and so on. And then it definitely has advantages over using some track robotic systems in precisely things like traction, weight, forces to handle the facilities that we're going to see in the space in the future. So this is one of my favorite topics with NASA or with the Navy and so on and so forth. So hopefully we're going to have more real-time robotics through a lot of the incredible work we're seeing in this workshop. That said, robotics is becoming expensive. We need larger laboratories. We need companies to help us integrate it and so on and so forth. Greg has done a lot of good work here, Dong Hyun and JB, Rachel, Steven, Jung Hyuk, Orion, and many people from the company. So I just want to thank everyone and thank you all for being here.
We have time for one question, unfortunately, if there is any. Questions? No?
So what is the approximate payload that you can carry with the exoskeleton? So how much of a help do you want to give to people that use it?
So backpack-wise is 30 kilograms. That's on top of the weight of the exoskeleton, which right now sits at also about 30 kilograms. So 70 kilograms payload. Batteries are not included, so that's something to consider. And then there's a discussion about whether combustion engine is, if you want to run, the set target for exoskeleton is 6 hours. So you probably need a gasoline engine, fuel cells and other things will come afterwards. You can assume that for payload it's the same thing. We're lifting boxes, 30 kilograms. So it's a mid-size, I call it heavy duty payload, but of course it's not entirely a human forklift. There is a discussion of whether a human forklift should be worn in the same way when you augment much the forces, especially because falling down is very important. So one aspect of this research actually involves as well doing corrections and predictions of whether we're going to fall down. And that's also exciting as a research thing, but right now, that's where we stand, about 70 kilograms in total payload.
All right.
Thank you for asking the question.
Let's thank Luis again.